Okay, today on 6.2, we're going to find and use the incenter and the circumcenter of a triangle. And you've probably never heard of what those are, but we're going to discover it here together. So what I want you to do is you're going to go to, hopefully you did this last time and you're already familiar with it, but go to geogebra.org/geometry, or if you have the GeoGebra app, you can bring up their geometry. And you're going to make a triangle. I want you to construct all the perpendicular bisectors of each side of the triangle. And then I want you to find out if they're concurrent. Concurrent means that all three cross at the same point. So I want you to pause this, go ahead and do that. When you unpause it, I'll run through it really fast so you can see how it's done. And then we'll talk about some of the attributes or characteristics of perpendicular bisectors. Okay, so I'm just going to make just a random triangle here. Doesn't matter what it looks like. Okay, and then I want to construct all of the perpendicular bisectors of each side. So if you go down to the More menu, down to Construct, and we have Perpendicular Bisector. Here's the directions, right? Select 2 points or one segment. I'm going to just select that segment. There's one perpendicular bisector. Select that one. Remember, the perpendicular bisector cuts it in half. So this segment is equal to that segment, and it has to form a 90-degree angle. And the last one, I'm going to do this one right here. And what we should find, like the next one of the questions asked is, was it concurrent? So by concurrent means, it means do all three angle bisectors cross in the same spot? And you can see that they do. And I can move my triangle around. And you can see that no matter where I move it, it's going to be in the same spot. Now, interestingly enough, right, this is an acute triangle. All angles are less than 90 degrees. If I make it an obtuse triangle, we're going to see what happens. So before we do that, I want you to add this to your notes. That point that I just showed you where all of the perpendicular bisectors meet is called the circumcenter of the triangle. This is the important thing that you should know. So add this to your notes also. The circumcenter is equidistant from the vertices of the triangle. So it's the same distance from all the vertices. So if we go back to here, if I were to, so first of all, this is the circumcenter right there. I'm going to put a point there. So that's the circumcenter. And then the other important thing is that, remember with perpendicular bisectors, as I travel along that line, it's always equal distance from the two endpoints. That was one of our theorems from the first section. This line is always equal distance from those two endpoints, A and C. And this line is always equal distance from those two endpoints, A and B. So if you find the point where they cross, that's the point that's equal distance from all three endpoints. Well, those endpoints all are the vertices of the triangle. So if I take this and measure, I'm going to make a little segment here. So I'm going to click on segment. I'm going to go from D to C. Then I'm going to measure that, but let's make all the segments first. I'm going to go from D to B, and from D to A. Then I want to measure each of those. I'm actually going to go back and I'm going to make each of those into a dashed line. And we can kind of tell the difference between it and those perpendicular bisectors we already had. So I'm going to measure each of those lines. That's a distance from that middle point, from this, we call it the circumcenter, right? The circumcenter of the triangle and the endpoints. Now I'm just going to measure each of those. So I come down to the measuring thing, measure a length or distance. I'm going to measure that one, and that one, and that one. They all come out to be 3.9, right? They have the same distance. Now I'm going to grab my mouse. I'm going to move it around just to make sure that's always true. So I'm going to drag this triangle around. You'll see that no matter where I move it, they're equal distance. Hey, the second part of that question I asked is, will the circumcenter always be inside of the triangle? And we just saw, if I make it an obtuse triangle, your circumcenter can actually, the perpendicular bisectors, right? That one, and that one, and that one actually can cross on the outside. Interestingly enough, if you make it a right triangle, see if I can do this. If you make it a right triangle, so this angle right here is 90 degrees, the circumcenter actually ends up being on the hypotenuse of the triangle, right on the midpoint of the hypotenuse of the triangle. So when you kind of mess around with that, kind of see those relationships, the main things you ought to know is the circumcenter can be on the inside or the outside, or actually on the triangle, if it's a right triangle, and that the circumcenter is always the same distance. So you can see there that those points are all this where I stopped right there, right? The distance from each of those, that distance, and that distance is all 4.7. Okay, it's equal distance from the vertices of the triangle. And one last kind of cool thing before I go on and go through the theorems is that because it's equal distance from all those endpoints, you can actually take a circle. So I'm going to make a circle. So I construct a circle at the center. I'm going to start it at D. And I'm going to go out to one of these vertices. I'm going to go to C right there. And you'll see what happens is because that center point is equal distance from all the endpoints, the circle is inscribes, or if it's on the outside, you can say it circumscribes the triangle. That's one of the reasons why they call it the circumcenter. So it's always equal distance, so you can form that. So kind of cool. You can end up with, no matter where you go, right, that circle will always circumscribe those 3 points. And the reason why, right, is because that distance from the vertices is the same, which means it's really the radius of the circle. So that's kind of cool. Okay, anyway, let's get back to the theorems and the problems you're going to run into. So this is the type of problems you'll see on your assignment with the circumcenter. Here's the theorem, first of all. It's really simple. All it says is the circumcenter is equal distance from all the vertices of the triangle. So what all that means is that that distance and that distance and that distance right from that circumcenter is all going to be the same. This first problem says then 3 snack carts sell frozen yogurt from points A, B, and C outside a city. Each of the 3 carts is the same distance from the frozen yogurt distributor. Find the location of the distributor. Okay, so what we're going to do is construct all the perpendicular bisectors, and I'm not going to get out like a compass and stuff and do that. I'm just going to approximate. So if you look at this, that's about the midpoint. That would be the perpendicular bisector. If you look right here, about right there is the midpoint. That would be the perpendicular bisector. It's hard to tell exactly, but there's something like this is my perpendicular. So that point where they cross would be equal distance from point A, from point B, and from point C. So that would be the location of the distributor. Now again, that isn't perfect because I didn't get out a compass and actually construct the exact perpendicular bisector. We're just going to ballpark it there. So this is a similar problem. It says 3 snack carts sell hot pretzels from points A, B, and E. What is the location of the pretzel distributor if they're equal distance from the 3 carts? So again, if we're going to do it perfectly, we'd construct the perpendicular bisectors. I'm just going to draw the sides. We're not going to, though. We're just going to ballpark it. So there is the midpoint perpendicular bisector. Midpoint perpendicular bisector. Midpoint, so that point right there is the circumcenter. It's equal distant. I'll do this in a different color. It's equal distance from each of those endpoints around there. This one says, find the coordinates of the circumcenter of ABC with vertices A0, 3, 0, -1, and 6, -1. If they have the picture for you, it's not bad. All you're going to do is construct actually they kind of already did it for you here. My apologies. But let me just go through this. If here's point A and there's point B, this is the midpoint. So that bisects this side AB. And you have to draw the line that's perpendicular. Because it's vertical, it would be a horizontal line going that way. And then if you take this bottom side, it goes from 0 over to 6. So if I go halfway is 3. And you draw the perpendicular bisector. I don't have to do the third one, right? Because we know that all 3 perpendicular bisectors are concurrent. So if I find where 2 cross, I know where the third one crosses to. That's right there is your circumcenter. So it is the same distance from, if I measure this distance, it's the same distance from A as it is from C as it is from B, if I measure all 3 of those distances. So I could also draw a triangle, or circle, excuse me, that's circumscribed around it. This will probably be bad. But if I take this circle, something like that, that would be the center of the circle where the circumcenter is, and it's the same distance from those 3 points all the way around. Let's just do one of these. You guys try 2. If you don't have to do this on graph paper. If you do, it's a little bit easier. But take those points and plot them. See if you can find where the circumcenter is. Okay, so if I do number 2, the point -2, 5 is right there. -6, 5 is right there. and negative 2, 1 is right there. So this is my triangle. Because it's a right triangle, and one side is vertical and one side's horizontal, that makes it a lot easier. So I'm going to come up here. This goes from, let's see, 1 to 5, so halfway would be 3. And then I want the line to be, my perpendicular bisector has to be perpendicular, so it has to be a horizontal line. This one goes from negative 2 to negative 6, so the halfway would be negative 4. Okay. And where those two cross at right there is the circumcenter. So that point is negative 4, 3. Okay. So circumcenter, main things. One is that you find the circumcenter by constructing the perpendicular bisectors. You also want to know that the circumcenter is equal distance from the 3 vertices of the triangle. And the last thing is just remember, if it's a right triangle, it will always be on the hypotenuse. So it'll end up being, if it's acute, it'll be inside the triangle. If it's obtuse, then it will be on the outside of the triangle. Okay, now we're going to discover what the incenter is. So I want you to go back and do a similar thing. You can pause this, open up GeoGebra, make a triangle. This time construct the angle bisectors instead of the perpendicular bisectors, and then find out if they are concurrent. So I have hopefully you had a chance to do that. I'm going to run through it really quick with you. I have GeoGebra up here. Just remember, if you go and make a new and you don't save, it'll open up just a blank page here. So again, I'm going to construct just a random triangle. It doesn't matter if it's acute, obtuse, or right. And then now I'm going to construct the angle bisector for each of the angles. So if I come down here under construct, right here is the angle bisectors, right? Select 3 points or 2 lines. I found it's usually easier to select 3 points, so A, B, and C. Sometimes when you select the 2 lines, it does funny stuff. So there's one angle bisector. That was the bisector of angle B. Let me do the bisector of angle A. That is the bisector of angle A. Now we're going to do the bisector of angle C, and we're going to see if they're concurrent. And you imagine that. Crazy stuff, right? They are concurrent. And you'll notice I can take that triangle, and it's not just for this one triangle. It doesn't matter what I do with it. I can make it an acute or that looks like it's about a right triangle there. Or you can make it an obtuse triangle. They're always concurrent. Something else to notice is, remember with the circumcenter, sometimes the circumcenter was outside the triangle or on the right triangle, on the hypotenuse. The incenter is different, so if it kind of makes sense, if I take all of the angle bisectors, they're always going to be inside the triangle, always. So no matter where I move that, I can make, no matter what kind of triangle I make it into, whether it's obtuse or acute or right, it'll always be on the inside. Okay, let's remember what we know about angle bisectors. So an angle bisector, if I pick a point somewhere, and say I pick a point right here, doesn't matter where it's at, if I measure the distance from this side and this side, it has to be equal distant. Now if I pick a point over here, it has to be equal distance from this side of the triangle and this side. If I pick a point over here, it has to be equal distance from, it has to be equal distance from this side and this side. So if I take all of those points, right, all those points then that has to be equal distance from these 2 sides. I did the wrong one, I'm sorry. Let's take that, I'm going to delete that point. I should have put one over here. So this point, F, is equal distance from side AB and side AC. So if I keep going out till I get to there, this point G is equal distance from this side and this side. So if I keep going till I get to there, and this point is equal distance from that side and that. So when I get to that point, what that means is this is the point that's the same distance from the sides of the triangle. So it's important we know that. This is no longer equal distance from the vertices of the triangle. This is equal distance from the sides of the triangle. I'm just going to delete those points. So if I take this and measure it, if I come down here, and this is a perpendicular line, remember when you measure the distance from this point to the side, you measure the perpendicular distance. So I'm going to do the perpendicular bisector, actually perpendicular line, not bisector. And it says select a point in a perpendicular line. So I'm going to go from here to there. Okay, and then I'm going to, let's see, put a point here. and I'm going to make this a segment from there to there, and then I'm going to delete this bigger line. No, that didn't work. Let me try that one more time. So I'm going to do that again, the perpendicular bisector. Oh, not the bisector. Sorry, I'm struggling a bit here. Let me try that one more time. Up here, there's a gray button. If you're like me and screwed up, you got the undo button. So let's undo that. I don't want the perpendicular bisector, I just want a perpendicular line. So I want to go from here over to there. And then if I measure the distance, right, if I put a point right here, and I measure the distance from here to here, from E to D, that distance right there is the distance from the center to the side, the perpendicular distance. So I'm going to make that a segment. Actually, let's just do this. Let's just measure that distance down here. So I'm going to come down here to measure length. I'm going to measure from D to E. Now this is going to get a lot of confusing. This is going to get really confusing because there's a lot of lines. But let me just show this to you really quick. If I make the perpendicular line from there to there, and I put a point on it, put a point there, and I measure that distance. So I'm going to measure that distance there to there. Hey, it's the same distance. So the distance from D to F and D to E is the same. We've got one more to do. We'll come down here and measure the perpendicular line. Now measure from there down to this side and put a point there. Okay, and we're going to measure that distance. So what we should show is that in center, where the angle bisectors cross, they all cross the same point. Now this looks confusing because there's so many lines, and I apologize for that. But the big idea is this. In center, the way you find the in center is you make the angle bisectors, and you find where they all cross at. They will always be concurrent. What we know about the in center, that's always equal distance from the sides of the triangle. So remember, with a circumcenter, we could draw a circle around the triangle. With an in-center, you can take a circle and go to the center point. And if you go out to there, you can draw a circle that's inscribed inside of the triangle. So it's always that same distance. So if I take that, I'm going to delete some lines here. Okay, so big ideas. In center is where the angle bisectors cross. So go to here. Right? The point where all the angle bisectors meet is called the in-center. It's equal distance from all the sides. So you can take it and you can draw a triangle, a circle that's inscribed inside of the triangle. Is in-center always inside, outside of the triangle? It's always on the inside, no matter where you move it. That's where the angle bisectors will always cross. Okay, here's the actual theorems that you'll use on the assignment. So if you have the in-center, this is the in-center, right? So this is the angle bisectors, angle bisectors, angle bisectors. If it's the in-center, then the distance from point P to this side over here, will be the same as from point P to this side, which is the same as the distance from that point to this side. Okay, it's equal distance from all the sides of the triangle. Okay, so here's what some of your problems in your assignment might look like. Because in the figure shown, ND equals 5x minus 1. So ND, that's this side right here, is 5x minus 1. And NE is 2x plus 11. So this side right here is 2x plus 11. And it wants me to find NF. Okay, so a couple things. Notice up here, each of these lines, that is an angle bisector, right? That's an angle bisector, and that's an angle bisector. That makes this point the in-center. That means that all of these segments are equal. They have to be. They have to be the same distance from the sides of the triangle. That's what an in-center is. So if I know these two are equal, there and there, I'm going to go 5x minus 1 equals 2x plus 11 and solve that. So I could minus the 2x over. I could add the 1 over. So x equals 4. It wants to know how long this side is right here. So I'm going to plug 4 back into these. So if I plug 4 into there, it'd be 5 times 4 is 20 minus 1 is 19. Right? 2 times 4 is 8 plus 11 is 19. So this is 19, 19. This one has to be 19 also because those are all congruent. They're all the same distance from the sides. It says, can NG be equal to 18? Explain your reasoning. Let's see, NG. Could this be equal to 18? So this is kind of a weird question. It doesn't really have anything to do with incenters. But if we know that this one is 19, remember that the perpendicular distance is the shortest distance. From that point to this line, that's the shortest distance. This one's going at a diagonal over here. It has to be longer than 19 then. It could not be 18 because it's a diagonal. The distance is measured at a diagonal, which is going to be a longer segment. Okay, here's another one. You guys pause this and try this one really quick, and then you can check it with what I do. We know this is the incenter. Notice how it only drew 2 on this one, but that's okay because we know that all 3 will be concurrent. So if I know where 2 of them cross, I know that the third one, if I were to draw this one over here, it would cross the same spot. Okay. That means we know that each of these are equal, right? Because that's the incenter, it's equal distance from the sides. So it gives me QM and it gives me QN. I can set those equal. 3x plus 8 equals 7x plus 2 and solve that. What do we get? 4x over here and minus the 2 over 6 over here. Divide by 4. Divide by 4. So 3 halves or 1.5. And then it wants me to actually find QP. So it wants me to find out how long this one is right here. So I actually need to find out how long those segments are. Plug 1.5 back in. 3 times 1.5 is 4.5 plus 8 is 12.5. Okay, this is what that ought to come out to be. Okay, we'll do this last problem here. It says a city wants to place a lamppost on the boulevard shown so that the lamppost is the same distance from all 3 streets. Should the location of the lamppost be at the circumcenter or the incenter of the boulevard? Okay, this is the important part. It says it wants it to be the same distance from all 3 streets. So that means it wants the same distance from here, and from here. So you got to remember, this is the important part. This is where it gets hard, is because we're going to have lots of theorems, just like the last chapter, and there'll be lots of things to remember. The circumcenter is the same distance from the vertices of the triangle. So it would be the same distance from this point. We'll do it a different color. It'd be the same distance from the vertices, from those points and those points. The incenter is the same distance from the sides of the triangle. Right, so in this case, from the sides is the incenter. Okay, that means we're looking for the incenter because we want the point that's the same distance from the sides. So if you're going to find it, you would construct the angle bisectors. You would come up here and you would draw the angle bisector. You draw the angle bisector. Find the point where they cross, that's the incenter. It would be the same distance from all the sides of the triangle. Okay. This assignment's pretty easy, but the key thing is make sure you've memorized these. So you got to know the circumcenter, you draw the perpendicular bisectors, and you find the point where they all intersect. That's the circumcenter, and it will be the same distance from the vertices. Did they say circumcenter? Circumcenter is where all the perpendicular bisectors cross, and it's equal distance from the corners of the vertices of the triangle. The incenter is where all the angle bisectors cross, and it'll be the same distance from the sides of the triangle. Thanks, guys.